Hello, my name is Victoria Grimes, and this is my Lab 2 for the motion of a falling object. The purpose of Lab 2 was to formulate an experiment to analyze the motion of a falling object, observe the object falling with a tracker application, analyze the impact of gravity and drag on the falling object, construct computational models based on the foundational principles of Newton's second law, and then compare the models with observations and draw conclusions about the effects of gravity and drag. The fundamental principles and models in Lab 2 were Newton's second law, which says that an object's change in momentum is dependent on the net external force, and it relates the net interaction between system and surroundings to changes in momentum or motion of the system. For drag, this is a force whose direction is always opposite to the direction of the object's motion and has a magnitude that is proportional to the square of the distance. And for drag, this is happening because as the object falls, it is interacting with other particles, for instance air, who slow down the object's motion, and these equations are presented on the right-hand side. The first one is the formula for drag, and there's a proportionality constant, which we will be calculating later. And also seen here is the formula for the gravitational force, which we will also need to use for the code later. And we have our velocity and position update formulas, which are also used in the computational models, and we discussed this in an earlier lab. The video on the left, as you can see, is a simple video of me dropping a plastic elephant figurine from rest. The video on the right is where I put the footage into Tracker to get the position and time information that I later put into the computational models. Shown here is the position versus time graph for the observed motion of the elephant. This slope is not constant, i.e. a straight line. It is instead curved, meaning that the object is accelerating. I inserted these values into the computational models based on data I received from implementing the Tracker application. For the code, I inputted the information from the previous slide into the WebV Python to create this computational model. As you can see on lines 77 and 79, the update velocity and position formulas were used to calculate the elephant's velocities and positions at each timestamp. Also, this first model only includes gravity as the force acting on the falling figurine. This is ensured by making sure the proportionality constant B is equal to 0 and making F net just the force due to gravity, as we can see down here. These are the results from the model with gravity only, which also displays a parabolic-like slope. This implies that there's another force acting on the object as it falls. This is the code for the computational model, including the drag force. The proportionality constant was found with trial and error to get a final position closer to the observed data, and this force is in the opposite direction of the gravitational force, and all of your initial conditions stay the same. The graph here accounts for gravity and drag, which you will see in the next slide is closer to the observed data for the experiment. Presented here are the observed data and computational model graphs. The gray line is the actual observed data, the pink line is the data from the gravity-only computational model, and the brown is the data from the gravity and drag computational model. As we can see, when we accounted for drag, we got a final position closer to the observed data, since the pink's final position is much lower than the brown's final position. We've now reached a conclusion and discussion. So, which models predict a terminal velocity? The model predicting terminal velocity is the gravity and drag computational model pictured on the right. When in terminal velocity, the force of drag pointing up has exactly balanced the force of gravity pointing down. What does this mean for the net force? This means that as the terminal velocity continues to infinity, the net force would eventually become 0. This would imply constant velocity motion after a certain point, and the velocity would not change. To observe this, I modified the code to run longer. Another question that we can ask is that if the object were thrown downward initially, does the terminal velocity change? And the answer to this is no. The terminal velocity is solely based on a relationship between the downward force of gravity and the opposing drag force, and it has nothing to do with the initial velocity. So therefore, if our falling object had an initial velocity and it wasn't at rest, the terminal velocity would still be the same.